Okay. Where are we? We are like 80. Okay. Sorry for late start. So any question? I think this time we go over this. This time we go over how to do inverse Z transform, and also some geometric interpretation of Fourier transform by just looking at the point zeros of the Z transform and thinking about the Fourier transform just being the Z transform on this unit circle with pi from 0 to, with omega from 0 to 2 pi. Okay, so that's geometric interpretation. And if you don't have a question, then let's go to the properties of Z transform. I don't know if we have. Okay. Anyway, let's see how much we can do. So yeah, properties of Z transform, and this is kind of similar to Laplace transform, where we need to consider the ROC, how ROC change when we do all the properties. And also this is a bit like discrete time Fourier transform, because you always know that the Z transform on the unit circle is a discrete time Fourier transform. Okay, so let's see the first property, linearity. Just as usual, Z transform we have linearity. So A small x1 plus B small x2. We do Z transform and it becomes A big x1 plus B big x2. And ROC, just like in Laplace transform, it should be the intersection of the first ROC and the second ROC. But we also say containing because you can cancel some poles there. So it's at least this intersection, but you can also expand if some poles at the boundary got cancelled out. Okay. Okay, so that's an easy one. Then the next one is time shifting, so we skip the proof. But I guess you can kind of see this from the Fourier transform. So you do some discrete time shifting on this x. So x becomes x over minus n0. Then the corresponding Z transform, you get this extra z to the minus z, z to the minus n0 factor. So there's a z to the minus n0 times big X of z. And the ROC is basically the same, except that you are multiplying this z to the minus n0, so it can be a pole or a 0 at z equal to 0, depending on where n0 is bigger than 0 or less than 0. So ROC is the same ROC, but some point 0 might get, excuse me. So this might be 0 at either 0 or z equals infinity. So you need to check again your poles and zeros at 0 and infinity. And yeah, just from this z to the minus n0. Okay. So that's an easy one. Then we have scaling in the z domain. And well, the formula is easy. So the formula is quite simple like this. So it says that if we have z change to big X of z change to big X of z divided by some whatever complex number n0, z0. Then on the x side we have z0 to the n times your original x of n. And ROC will be this absolute value of z0 times your r. So you will scale your ROC like inside or outside. So if this absolute value of z0 is non-zero, then you are scaling this either inside or outside. And so it's scaling in z domain, but it's actually kind of like z shifting, although it is scaling of z, because I guess it's more like the s shifting, so it's like a frequency shifting. Because you think about z equal to e to the s, so if you get like a constant shifting in s, then that's like you multiplying z with some number, right? And the other way to see this is that you remember in the Laplace transform we have this s shifting, so s change to s minus s0, then you get this extra e to the st factor, and this e to the st factor is a little like this z naught to the n factor. Okay. And yeah, it's just because the S and the Z has different geometry. Like S, everything is strips, and the Z have those circles. Okay, and yeah, so to give you some idea about this rescale ROC, so basically everything you get multiplied by z0. So if x of z has pole 0 at z equal to a, then this thing has pole 0 at a times z0. Okay. 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 Oh yeah. Yeah. So everything gets multiplied by the z0. So if the z0 is bigger than 1, so you have the original ROC. So if this is 2, then your ROC will be like twice as big. So anyway, and the special case of this is, so we have been talking about like stretching or shrinking ROC for this absolute value of z0 being bigger or less than 1. But if the absolute value is 1, so we can also have a z0 just being a pure imaginary exponential pure imaginary, so just e to the j omega 0. And in this case, so the ROC, so the ROC doesn't change because the absolute value of 0 is equal to 1, but the pole and the zeros got shifted because we still have this pole and the 0 got changed to z0 times a. So basically they got rotated. And you think about this corresponding to the discrete. And yeah, and if you write it out, you see that you have x of e to the minus j omega naught z0 equal to this e to the j omega naught n x of n, and you see that this is very similar to the frequency shifting property when you are doing discrete time Fourier transform. So by multiplying this e to the minus j omega 0 is like changing omega to omega minus omega 0. So this is frequency shifting, and because z is e to the j omega. And then understand as the frequency shifting thing we have in the in chapter 5, that we get this hy e to the j omega 0 term. And here are some pictures to show that the pole and the zeros got shifted when you are multiplying this e to the j omega 0. So we have the original x of z with 2 0 here, 0 here, and the pole here. And when you get multiplied by this e to the j omega 0, then everything got rotated by this omega 0. And so the poles got rotated up here, and the zeros got rotated up here. Okay. So yeah, so this is the scaling in z domain, and it corresponds to frequency shifting or s shifting. Okay. Because z is like exponential base, so addition in s is a multiplication in z. Okay. And then we have time reversal. So yeah, so time reversal also looks a little weird. So if you get a negative sign on tan, which is n, so x of minus n is z transform is big X of 1 over z. Okay. So you see this a bit weird exponential thing in the s. Then so here we have a comparison in the Laplace transform. We have minus in t, then we get minus in s. Minus in s actually means 1 over z. Okay. And ROC is 1 over r. And yeah, so basically all the pole and the 0 got inverse. You have a pole at say a. Okay. And yeah, so say you have a pole at z0, then you will become a pole 0 at the 1 over z0, etc. Okay. So that's a time reversal. And then more more modification in time, we have this time expansion. So remember in section 5, in chapter 5, we have this weird discussion on time scaling being weird in discrete time, because in discrete time, well, time is discrete, you can only take value in those integer values. So you cannot really scale your time with non-integer values, and we say that the only sensible way we know to do time scaling is define this x sub k function. So we have x sub k function basically stretch all. So if x of n look like this, then x sub k of n is like stretching all this function by a factor of k. So say we have an example of k equal to 2 here. And then this bracket 1 will get stretched out to this bracket 2, and this bracket 2 gets stretched to 4, etc. And in the middle, the empty part we just fill with 0. Okay, so this is the only time scaling we know how to do in discrete time case. Okay, so anyway, we can do this x sub k of n scaling to the function in time. And then we can think about what is z transform is, and it has this nice formula. And once again, we skip the derivation. But so x sub k of n, we say we can that is z transform is this big X of z to the k. And the ROC is a bit funny. ROC is r to the k minus 1. And well, so these are two meanings. So if you're just looking at the area of the ROC, then basically means that well, the boundary gets multiplied by a factor of not really a factor. The boundary of the ROC gets taking this 1 over k root, right? So it's going to get closer to 1. But also this is a bit more general. We also have that if x of z, so the original function, the original z transform has a polar 0 at a, then then x of k will have a polar 0 by taking the k 1 over k root. Okay, so it's a bit funny. And maybe we can draw a little picture. Okay. So we are kind of like compressing things. So if we have, let's say this is a unit circle, and let's say we have a pole here, right? And so we have some radius and some angle, and then we do this 1 over k thing. Then it will get, so if it's outside, then the radius get like 1 over k. So radius will get smaller, and also its angle, so this omega angle will also get 1 over k. So it will become somewhere like this. Okay, and you can see that. So say if k equals 3, then all the omega get divided by 3. So all your pole 0 will get like so say if k equals 3, maybe, then all the point 0 will get compressed into this at least 1/3 of the plane. Okay, that's when you do this 1 over k thing. Okay, and okay, so that's a bit funny. And then we can so we say we don't have a proof, but we can kind of semi-check that this is correct. So remember that we have x of z, it can always, well, this is by the definition of x of z, and we can interpret it as a power series expansion in z, right? So big X of z is x summation x of n times z of z to the minus n, with n from minus infinity to plus infinity. And then we can think about what's this big X of z to the k. So so we put z to the k as z here, then the summation x of n z to the k to the minus n, then obviously this is z to the minus kn. And then we see that this is actually equal to what we want, right? We want it as this x sub n, the z transform of the x sub k of n. And let's change the dummy variable, so let's say it's so let's distinguish between m and n. So let's say x sub k, the z transform of x sub k is x sub k of m and times z to the minus n from minus infinity to plus infinity. And we see this thing as this thing has the same property that we expected, because here we have z to the minus kn, right? So the power here, so n is integer, so here the power of z is the integer multiple of k, right? So in this summation we only have like kn, integer multiple of k as the power of z. So this thing, the m is multiple of k, right? And so here we have that, and here we have the same thing. And because you remember this x sub k of m only has value when m is only when m is multiple of k. So you see that they both have only have terms when the power of z is integer multiple of k. So yeah, integer multiple of k. And also you can easily check that the coefficient actually match. When is n equal to 1, then is x of 1 here, and that will correspond to m equal to k. And when m equal to k, then you have x sub k of k is x of k divided by k, which is x of 1. Okay, so you see that this matrix is what you expected. Okay, so yeah, here is a semi-derivation of why this is true. Okay, so this is a bit weird property of time expansion. Question? If not, then let's see the next one. So conjugation. Conjugation thing is not weird, it's just like before. So, but also we don't have a derivation. But anyway, so if you conjugate x of n, and then in the z domain you have those kind of double conjugation. So x of n become x conjugation of n, then big X also get conjugation, big X get conjugation, and the z also get conjugation. So I guess you can derive this from the definition probably. So yeah, if you conjugate this part, conjugate everything, then you should get the thing. Yeah, and just as before, if you have conjugation, then you can do some derivation on what happens when your signal is real, which is pretty useful because a lot of physical signals are real. So you can check your z transform. So anyway, if x of n is real, then obviously this thing should equal to this thing, right? Because x of n equals to x star of n, then their z transform should be equal. And yeah, so what you get is big X of z equal to big X star of z star. And then a slightly more useful form is you do complex conjugation on both sides, then you get big X of z star will equal to x star of z, big X star of z. Okay. And so this tells you something about the polar and zeros in x of z, which is kind of very expected. And it says that if x of z has pole 0 at z0, then it must also have a point 0 at z0 star. So all the point 0 form conjugation pairs, and you can check from the previous examples that this is actually true. And let's see, again, the derivation should come from here. and it says that okay, so x start of z0, z start. So at z0 start, the big X value equal to the big X value conjugation, right? And so if z0, if big X of z0 is a 0, then this is a 0, then if you take conjugation it's still 0. So you know it is a z0 start is 0. And also is pole and infinity conjugation is also infinity. So yeah, just like before. From here you can see that the pole and the 0 form conjugation pairs. Okay. So yeah, I guess it's a little different by it being not different to the Laplace transform. So Laplace transform we also have this property, and here even though the geometry is changed to a circle, we still have those conjugation pairs, and the conjugation just reflects around the real axis, right? So the point 0 still form kind of pairs like this. So they also still form pairs like this, etc. So they, even though we are a lot of things we are thinking about them on a circle, for real signal, point 0 still form these conjugation pairs. Okay, so that's that. And then the next one is the convolution property, and here not too much more to say. Basically, just saying as always, you have the convolution on the time domain, then you get the multiplication in the z domain, and and RC just as usual, it should be the intersection of two RC, but if you cancel some point 0 because you have multiplication, then it can be bigger, and that is derived in problem 10.56. Okay, and but still as usual, from the convolution property, we can derive something. And here we use it to get the difference property. I think. Yeah. Anyway, so we consider this LTI system. Y of n equal to h of n convoluted with x of n, and now we use this h of n, which will give us the difference between x of n. So h of n is delta of n minus delta of n minus 1, and so we want to use convolution property here. So we want the z transform of this h and the z transform of this x, and so first the z transform of h. Well, it's a linear combination of a very simple terms, delta and delta, and we know the z transform of delta are just powers of z. So this is 1 and this is z minus 1. Okay, and okay, so if you think about this thing, then you can also express this as a rational function, and it has a pole at 0 and 0 at 1. Okay. Okay. And then we think about the z transform of x of n. So x of n z transform to some big S of z with some LCR, which is very generic. And then by our convolution property, the z transform of y will be, so the algebraic part will just multiplication of the two z transform. So this thing and this, so you have this 1 minus z minus 1 big X of z. And the ROC, okay, so we skip you one line here. So the ROC of those delta function transform is the entire z plane except the origin, because you just look at this thing is converging everywhere except this point z equal to 0. Okay. So you have intersection of this R with everything except of 0. And yeah. And so the ROC is basically R, except that this point z equal to 0 might do something and delete z equal to 0 from your R, or the 0 might also delete the pole of R, so you might you might delete the point z equal to 1 and extend your RC, etc. Okay. But if there is no pole cancellation from 0 and 1, then the RC is just R. Okay. And anyway, that's why. But as we say, we can also think of this as the difference property, because if we actually do the convolution is very easy because you are just convolute this delta function, and as we know, all the way back to chapter 2, if you do convolution in delta function, you just get back your same thing, or time shift over your thing. So delta convolute with x, you get x. Delta of n minus 1 convolute with x, you get x over n minus 1. So this is the difference of x, so, right? So 1 of n is the first difference of x, and this can be compared in continuous time, compared to the differentiation. Yeah. So this is kind of the counterpart of the differentiation property, which we listed here. So differentiation property is a dx dt, then its Laplace transform is s times big X of s. Here we get, so as usual in discrete time, the difference, we get this weird factor, this 1 minus z to the minus 1, instead of just the s here, which looks nicer. Okay, any question to the difference property? Oh, it's very hot. And okay, so that's the difference property, and so we derive the difference property as an example, and then we can, as usual, we have difference property that we think about is inversion, which is accumulation or summation property. Okay. And so we want to know that if we have some W of n is the accumulation of x, which is summation x from minus infinity to n, and this is equal to, as we know, this is equal to x of n convoluted with our unit step function u of n. And so the summation property, you can once again derive this using the convolution property. So you do z transform on both sides. Okay. And so you know the z transform of this thing will equal to the multiplication of z transform via u and z transform via x. And z transform of u, we actually know this is our favorite special case of our favorite example 10.1. This is exponential decay. If you just pick a equal to 1, then it's u of n. Okay? So a equal to 1, then you just have this 1 over 1 minus z minus 1. And the x over n obviously transform to big X of z. And we also need to check the RC. And RC should be intersection of the RC of x and the RC of z. So RC of x is whatever RC are. And but here now the RC of u is non-trivial. So the RC of u is z bigger than a, with a equal to 1, so this is z equal to 1. So RC should be the integration of r and z bigger than 1. And can get larger if you happen to cancel some poles and zeros. Okay. Yeah. So this is actually quite important, so mark out. So RC is non-trivial. Okay. And yeah, as we said, this is the counterpart of the, so this is summation, so this is the counterpart of the integration property, which has this 1 over s. That's big X of s. And here we also have RC. So RC is a similar thing. Here we have RC is the integration of r, and this is real x bigger than 0. and we have the same structure of RLC because this can also derive from the convolution between U and X of t. Okay, so here the U of n convoluted with X of n, and here this is U of t convoluted with X of t. So the RLC both have those intersection structure. Okay, so that's the difference and accumulation in the time domain. And then we can go to, then we go to a harder one, which is differentiation in the Z domain. So now this is really weird. Actually, okay, but if we don't actually have integration in Z domain because it will be probably very hard. But anyway, we have the differentiation in Z domain. So you see this d big xz dz here, and but this property is, as you can see, it's a bit weird. So dxz dz, and in before we just have like get the h bar n on x of n side, but for reasons I guess we have a very different part here. We actually also have the h bar z here. Okay, and yeah. So this is different from the Fourier transform formula where you only get the h bar n here. Here we also get the h bar z on our h bar small z on our z side to complete our differentiation property. Okay. Yeah, so it's a bit weird, and I think this can be derived here. Let's see, can we see this really quickly? Yeah. So if you think about you do ddz on this definition of big X of z, then you get minus n here, and this z also get -1 power, right? So if you want to get back the same power series, then you need to multiply h bar z to compensate your z to the -n become z to the -n-1, and also you will get h bar -n from this -n going down here. Okay, something like that. But obviously we didn't write down the exact formula, but you can probably derive it by doing differentiation of z on both sides and try to piece things back together into into a nice equation. Okay, and okay, and yeah, so that's the differentiation property, and let's see how it can be used. So let's see, actually pretty smart example first. So this example, we have x of z equal to this log of 1 plus a z minus 1, with RC being z bigger than a. And I think we see this before when we do power series expansion. But here we solve this with a similar but different way by using our differential property. And so we have this log here, and if we want to do inversely transform on this thing, then well, this log is very annoying because it's not a rational function anymore. So as we see before, we can do power series expansion, but now we can also deal with the log by just doing a differential property. So we know this n x of n is the transform minus z dx dz. Oh, we didn't say that RLC didn't change, but yeah. Yeah, we want RLC didn't change, so that's also one of the reasons we want to multiply by z here instead of doing shifting n here. But anyway, so if we write it in this form, then very nicely RLC didn't change. And okay, and then we can calculate this minus z dx d big X dz. And so the big X dz, then this log will become like 1 over 1 plus a d minus 1, and with extra a factor. Oh, actually with a lot of extra factor. So let's try calculus very quickly. So dd log, so you have 1 over this thing, everything. Then you need to differentiate the inside thing with z. So you get a, and z minus 1 should give you minus a z minus 2. And so minus z minus 2 times this minus z becomes z minus 1. So you get this very nice form, or this very nice rational form of a z minus 1 over 1 plus a z minus 1. And with ROC being a bigger than z. Okay. And yeah, so you see that we get a rational expression now. Rational. And now we can get the inverse transform on this thing, which will actually use the property that we haven't talked about, but we'll talk about later, which is the time shifting property. Okay? And what we mean is that we want to make something look like this. Okay. So how do we make something look like this? So the idea is, if you don't look at the upper part, then it's something we know, right? It's something very similar to we know, because we know this. Wait, I'm a little confused. Oh, yeah. Yeah, so this is our favorite 10.1 example with a actually equal to minus a. Okay, so it's a little confusing. So we have the a to the n u of n become 1 over 1 minus a z minus 1, right? So this minus a, we have plus a here, so we actually have the minus a to the n here times u of n. And also this a, then we can just by linearity get this extra a here. So that's the same, and with the same ROC. And excuse me. And then okay, then we use the time shifting property, because here we also have extra z minus 1. So we get the time shifting property. We use the time shifting property to get all this z minus 1. And so here is the time shifting property. And it says that if you do time shifting, then you get this extra z2. So if you time shift with this minus n0, then you get this extra z to the minus n0. So we want extra z to the minus 1, so we want x over minus 1. So every n here should become n minus 1. So n become n minus 1, n become n minus 1. Okay. Then we can get this extra n minus 1. And also ROC, we say it's the same thing, except that this d to the minus z0 would be, we actually already talked about time shifting, sorry, I forgot. So let's see, talk about, yeah, sorry. We actually already talked about time shifting, I forgot this. Is in this 5.2, right? This is the second property, that because we didn't spend a lot of time talking about it. Yeah. So yeah, so time shifting, it says that if you shift the time domain with n0, then we'll get this extra power of z here. And the ROC is basically the same, but this extra z can change your point zeros at infinity or 0, so you need to be careful. And okay. Yeah, so using a time shifting, we can get this extra z minus 1. And so we know, so we feed the form of this a z minus 1 over 1 minus a z minus 1. And we know its inverse z transform is this a minus a to the n minus 1 u over n minus 1. Okay. And finally, we know this thing is n times x over n, right? This is n times x over n. And so x over n is just this thing divided by n. And so with a little more clean up, is minus a to the n over n and u over n minus 1. Okay. So this is a quite complicated example. Okay, question. And I believe, okay, so let's jump a little back. Let's see if we can find do we have the same example? Log. So we have here and okay. N minus 1. Yeah. So basically the same thing here, but here we didn't write a u here. We use this n from 1 to infinity. Okay. So you can see the minus 1 to the n plus 1 and this a to n. Okay. Oh yeah, actually we have the same expression here. So you check out with the previous calculation we get by doing the power series expansion. Okay. And okay, so next one is also an example using differentiation property. And so now this is things that we do in Fourier transform and Laplace transform. So we want to get extra power in our minus 1 minus a z minus 1. But unfortunately, this because we have a lot of extra factors, so this will give us a pretty ugly answer here. Okay. And so anyway, so instead of this thing 1 over this thing, we are doing inverse Fourier transform of a times z minus 1 over this thing square. So inverse z transform of a z minus 1 over 1 minus a z minus 1 square. And why is this ugly? Because we kind of know the answer. So we start with our like power of 1. So our favorite example of a to a n u1 and a z transform to 1 over 1 minus a z minus 1. And then if we apply our differentiation property on both sides, then this side become n a n u1, and this side this thing. And so this 1 over this thing, and you do differentiation, obviously you get like 1 over this thing square, but then you also get all the extra factor, and you calculate the extra factor, you combine with z, then you get a z minus 1. And yeah, so that's a similar calculation we have on here. Anyway, so you see that you do differential property on this, then you get this a z minus 1 over 1 minus a z minus 1 square. Okay, and obviously the same RC. So yeah, so this is what I derived. So the second order term is z transform back to also the power series with the extra linear term here. But you also have this weird upper term. So I guess if you want to do partial fraction expansion with higher power, then you need some weird trick to deal with this. And also we don't really derive this with higher order terms because it probably get pretty ugly. Okay. I guess if you do, yeah, if you do higher order terms, it's probably get more ugly. Okay. So yeah, unfortunately for the inverse z transform, we probably won't do too much higher order thing because all the extra term on the numerator can make your expansion very hard. Okay. But here is something you can in principle do. So if you can feed your second order term into this thing, then you can inversely transform to n a to the n u1. Okay. And finally, I think this is the last property. We have our initial value theorem. And will also look different. So it now has an even simpler form than what we had in Laplace transform, and it just says is the initial value x of 0 equal to z goes to infinity x of z. But we have the same condition, so also need x of n equals 0 for n less than 0. And the initial value theorem here is actually very easy to derive, because once again you just look at your because of z as a power series expansion. So with this causal condition, then you know that all the positive power disappear. And so as z goes to infinity, all the positive n term is z to the minus something. And so z goes to infinity, those terms should also all disappear. Then you are just left with this x of 0, n equals 0 term, right? So less than 0 term, so n less than 0 term, by the assumption they don't exist. And n bigger than 0 term, for z goes to infinity, they go to 0. So z goes to infinity, you just left with n equals 0 term. And yeah, so this is n equals 0 term. That's easy to derive. But we can say a little more here. That is, if our xz is a ratio of polynomials, so basically a rational function form, then we will have that no. Oh, yeah. Okay, so that's the derivation, and here we see that. So as a consequence, so if you have causal sequence, so you if you say satisfy this, and your x of 0 is finite, then obviously this is finite. Okay, so but also if your causal sequence and your x of 0 is finite, and also your x of z is expressed as a rational polynomial, so like p of z, or so like n of z over. Okay, so maybe it's easier to write down some equation here. So rational polynomial, so rational expansion as usual. So you have some numerator of z over denominator of z, right? Do I? It's me. That's the beginning of z, numerator of z, and over denominator of z. Yeah, and we still want z equal to infinity, this is finite. And that just means the power of z here should not be more than the power of z down here. Okay, so that's all I want to say. So the zeros cannot be more than the poles. And sorry, we're over time for 2 minutes, so let's stop and let's resume 10 minutes later. Okay, question? Okay, let's take a 10 minutes break. Oh, also it's very hot. You guys want to put on the AC? 高度。角度完了。Okay, let's start. Yeah, so that's the initial value theorem. The derivation is much simpler here. You just look at the power series expansion here, and you see that as z go to infinity, all the z minus n term go to 0, so you are left with this n equals 0 term, which is x of 0. Okay, and as the example, we see that initial value theorem we can use it to check whether our z transform is correct. So for example, we have in this example 10.3, we say that of x of n equal to this function, and our z transform is this function, and check the initial value theorem. And so as z goes to infinity, this thing all the z minus 1 term goes to 0, so it's just 1 over 1 times 1 equal to 1. And also we look at this, and we see that if we take n equal to 0 here, then it's just 7 minus 6 equal to 1. Okay, and yeah, so the initial value theorem work out x over 0, which equal to 1, equal to big X over z when z equals to infinity, equal to 1. And yeah, so that's actually all the property. So we here's the list of all the property we have for the z transform. So the linearity as usual, and time shifting as usual, and then there are transformation in z, which in the most general form is this big X over z over 0 transform to 0 to nx over n. And more based on the changing time domain. So if we have time shifting, then we have time reversal, give you z minus 1, and time expansion, which you need to do the weird x subcasing, and this give you big X over z to the k. And also conjugation as usual give you x star over z star, and convolution as usual, convolution in time give you multiplication in z. And first difference, which is a bit like a differentiation, and just like in discrete time case, just like in Fourier transform case, you can just derive that from the time shifting. So it's a linear combination of time shifting. 就给 y minus z minus 1. And then inverse of the difference is the accumulation, which you have this, which don't have weird extra terms like in the Fourier transform, but so you just get 1 over y minus z minus 1 here. So just inverse of this y minus z minus 1. And finally, we have this really weird property of differentiation, which you have a dx dz, but you actually need to multiply by minus z, and then you will multiply x side with n. And so here you can see that we are missing some property that we had in Fourier transform, just for reasons we don't have in z. And you see we don't have the integration property here. Well, I guess partially because z is not a complex value, so yeah, so I guess you also don't have that in Laplace transform because z is complex value, and yeah, when you do integration, you are doing weird counter integral. And also then we have initial value theorem here, but we don't really have final value theorem here. Okay, and you can think about why. Okay, so that's the properties. And also, just as usual, then we have the table for the transform pairs. And yeah, so those tables should be given in the finals, but it's a good idea. I think it's a good idea to memorize them a bit because they are useful properties. And anyway, so the z transform pairs, obviously we have the delta function give you 1, and the unit step function. I guess we should look at this first, right? So our favorite example 10.1 is a to the n u of n go to 1 over y minus a z minus 1 with z bigger than a ROC. And then the same thing with z minus a is minus a to the n u of minus n minus 1. Okay. And so as a special case of this phi, then we take a equal to 1, then if u of n transform to 1 over y minus z minus 1 with ROC z bigger than 1. And then similarly we have the other side u. Then we have a 6, special of 6 with a equal to 1. Then we have this minus u of minus n minus 1 is same z transform, and with ROC z less than 1. And then we have also a delta function, but with tangent minus n, and that's just z to the minus n. So the powers of z just transform to delta function at a different time step. Okay. Oh, yeah. And yeah, so the ROC is basically everything except that they will diverge either at 0 or infinity. Okay. And then, so this is like the first order partial fraction. Then we try to derive higher order partial fraction, but we see it's pretty ugly, so we only have this kind of second order thing. So from this phi equation, we apply the differential property, then we see that n a to the n u of n transform to this a z minus 1 over y minus a z minus 1 square. Okay, so yeah, it's not very clean, and so we don't derive a higher order of this. And but you can do similar thing, and you can derive the same thing with ROC being z minus a, and obviously you have this negative left-sided u. Okay, and then let's say we have those sine and cosine with u over n. Then this can be, I think you can just break sine and cosine into complex exponential and use property phi in a linear combination to get all of this. Okay. Okay. So that's the properties of the transform. Any question? And we are left with some time. Okay, so obviously we can finish the next part, but I'm not sure we can. Okay, let's see how much time we got left. Anyway, so yeah, so just like in chapter 9, then next we talk about basically the causality and yeah, basically we want to talk about the causality and stability of our system by looking at its system function. So for system function, just as usual, the system function or transient function is this big H, and it's the z transform of your small h. So it's the z transform of your impulse response h of n. Okay? And yeah, so we have a small y equal to convolution between small h and small x. And you do z transform, then you see that big Y equal to convolution of big H and big X. Okay? That's as usual. Our favorite system function equation. And then we see that we can analyze the causality and the stability of the system by looking at basically looking at the ROC of big H. It's very similar to the Laplace transform, except I think the derivation are now more rigorous because we are discrete time, so there are a lot of things, a lot less of things. Wait, that sounds weird. Much less of things that can go like divergent. Okay. Anyway, yeah. So you just look at h of z equal to summation h of n z of minus n, and so first thing you want to see is this causal. And so if it's causal, all the h of n is 0 for n less than 0, right? Oh, sorry. So here we will rewrite this as causal. So causal, the n less than 0 thing is 0, so we say n is summation from 0 to infinity. So we look at this, and we see that this thing should converge when so if it is converged at some z, then it should converge at a bigger z, because all the z has minus power. And also a way to, okay, so I guess there are two things we say here, sorry. So it's causal if only if the ROC is basically the almost possible ROC, so the exterior of the circle. And so that's one thing, and there is different thing that's including infinity. Okay, so basically there's 1 and 2. So there are lots of things to look at this. How should I say? So there is if only if, and let's see which direction I should say. So I guess let's talk about the only if direction. So if it's causal, okay, so the only if direction is probably harder. So if it's causal, then we want to say the ROC is the exterior and including infinity. So being exterior is a easier one. So it's just like in Laplace transform. So because it is causal, and so this is a right-sided function, right? So this is a right-sided function, so the ROC should be the outermost ROC. Okay, so this one, and but now there is something extra. So so in a Z transform ROC is very weird, right? So you can include or not including infinity, but here is causal, then it must include infinity, and and the including infinity you can look at here just by seeing that you only have like constant or negative power over z. So when z go to infinity, this is just basically the initial value theorem, right? So z goes to infinity, then this is just h of 0, and that should be finite. So excuse me. So you see that h of infinity is a finite value, so that should be inside ROC. And so that's the only if part, and the if part. If part everything, you basically do the same analysis. So you write your h of z as summation of those things, and let's see. And you know you are taking the almost ROC, so it's right-sided, and Also, if you include, so also actually it's probably easier. So probably just this will give you the if direction, right? So if your RC include infinity, then you know that you cannot have positive power here, right? If you have positive power here, then as z go to infinity, your positive power goes to infinity, and so so if you include infinity, then you don't have positive power. So if you also include infinity, then in this expansion you must summation from 0, and summation only from 0, then that just means it's causal. Okay. So here we can have a very rigorous derivation that this is causal if only if LC is exterior and include infinity. And okay, and so that's true for every system, but for rational system we can also turn those two conditions into two other conditions. Okay, so exterior condition in the sense, so we know that the LC must be the exterior of the almost circle. So if we think our rational function is something, some polynomial over some polynomial. And also it being include infinity, so once again just like the initial value theorem. So include infinity means that this polynomial must be less than this polynomial when z goes to infinity. So this upper polynomial must have smaller or equal power than this polynomial. Okay. So yeah. These two conditions turns to these two conditions if you are thinking about rational system. Okay, any question? Okay, if not, then let's see example. So we have this this system function h of z written very nicely already in partial fraction. So we have a pole at 1/2 and a pole at 2. And we are taking the almost LC z bigger than 2. Okay, and and yeah, so we see that the we are taking LC being the almost LC, so we know this is a right-sided function. And but this is also in rational form. So as we say that being almost LC is not enough. We also need to check the including infinity term. So this is in rational form, and so we can turn into, well, not quite rational form, but it's quite obvious that we can turn into rational form. So we can turn this into rational form and check whether this actually include infinity as LC. So we multiply everything and turn the negative power of z to positive power of z, and then we see the numerator has the highest power z squared, and the denominator has the highest power z squared. So as z goes to infinity, you just become 2, and so z goes to infinity, this is a finite value. So LC also including infinity, and yeah, and so we know this is causal. Okay, and yeah, both of degree 2, and this is causal. And we can also verify, because we have this nice form, we can do the inversely transform by just looking at the partial fractions. So this part transform back to this 1/2 to the n, and this part transform to this 2 to the n, and both with u of n. And yeah, so you see that both of them have u of n, and well, u of n is causal, so this is causal. Okay. Yeah, u of n make everything causal, and so this is causal. Okay. So here is the causality of the transform. It is similar to Laplace transform, where in Laplace transform you want the LC to be rightmost LC, and in Z transform you want the LC to be almost LC. But in okay, But Laplace transform is weird, right? So Laplace transform don't have if only if, as you only have if it's causal, so we only have only if. So if it's causal, then also is rightmost. But here we can have if only if because we can check the infinity. So we see that we also check the infinity point. Then the causality is if only if with those two conditions. And also including infinity, you can check easily when it's rational function. Because the rational function, you just take z to infinity, then you just count the highest power of the numerator and denominator. Okay, we don't have much time. Okay, so probably don't have time for unilateral transform. Anyway, so let's finish this stability. So yeah, stability. Once again, we can give a bit rigorous derivation here. So remember, stability is if only if h of n is absolutely summable, and since it's a discrete time, h of n being absolutely summable is if only if to the Fourier transform of h of n converge. Okay, because you don't have the all extra point where you need to fit the two extra Dirichlet conditions. So just this one condition give you that h of n converge. And anyway, so Fourier transform of h of n converge, then that means that the unit circle is in RLC, because the unit circle once again correspond to the Fourier transform of the signal. Okay, so we go the 3 steps derivation to see that your discrete time LTI system is stable if only if the unit circle is in RLC. Okay, which we say here. And here we spell what's unit circle. Unit circle is the absolute value equal to 1 circle. And yeah, so your RLC need to include a unit circle, maybe something like this. And this is similar to the Laplace transform case, where we say it's stable if only if your RLC include the imaginary axis. Although there the derivation is a bit weird because there are more divergence, but here we are pretty confident that this is true. It is stable if only if you include RLC include a unit circle. Okay, so let's see an example of this. And okay, so we are reusing our function here. So we have the same system function. H of z is these two partial fractions, so one point 1/2 and another point 2. And we are taking the almost RLC, and we already know the inverse Fourier transform is this thing. And okay, so this thing has 3 different possible RLC, right? Although here we already pick a RLC. And so the rightmost RLC, well, so it's the bigger than z bigger than 2 thing, then obviously it doesn't include this z equal to 1 circle, so this is not stable, although it is causal. Okay, as we checked before. Okay, and we can also see that from here that this is not stable because you have this 2 to n factor here, right? So 2 to n is an exponential increasing function, and obviously you sum this from 0 to infinity, it will diverge. And so yeah, so this is not a stable H of n. Okay. And but we say there are 2 poles, so there are 3 possible RLC. So we can look at the next possible RLC, which is z between 1/2 and 2. And as we see that your RLC is this ring between 1/2 and 2, then we'll include this unit circle here. And so this should be stable, but it should also be not causal, right? Because it's not the almost one. Okay. So this in between RLC should be non-causal but stable. And we can also check that by doing the inversion. And once again, we already have those partial fractions, and the inversion we just need to compare the RLC. So RLC is between those 2, so it should be outside this one. So this one should be the right-sided. Should get a right-sided inversion, and this one then RLC is inside this pole, and so when you do inversion, you should get this left-sided function is u minus n minus 1, and so the function you plotted, you kind of look like this. So on the n bigger than 0, 1 side, you get this 1 over 2 to the n decay, and for n less than 0, 1 side, you get this 2 to the n, which is also decaying when n go to negative infinity. So you have the two-sided exponential decay, and yeah, and this is actually absolutely summable because those are exponential functions. So you sum them is a geometric series and they converge. Okay. Yeah, so this is absolutely summable, and so this system is stable. So our criteria says it should. But also this is not causal because you see you have this n less than 0 part, you have all those weight here. Okay. And then finally there is a third possible RC, that's z less than 1 over 2 thing. So just inner one. Might not include 0. But anyway, so this is not causal and not stable because it's not almost 1 and it doesn't include this unit circle. Right? It's just a circle here. So yeah, so it's not causal and not stable, but it's something, and then we can do the inverse Z transform, and we see that Chauffin is this 1 minus 1 over 2 to n plus 2 to n with left-sided u of minus n minus 1. So actually anti-causal because it has no component and bigger than 0. But anyway, that's the Chauffin. And I guess we can check out this is actually not causal and not stable. So obviously it has a lot of things when n less than 0, so it's not causal. And it's not stable because it's 1 over 2 to the n term. This thing when n go to negative infinity go to infinity, so it's also not absolutely summable. Okay, so fit with what we expect. And finally we have the similar conclusion that we can arrive for rational functions that are both causal and stable. And so you see that we want to be causal and stable, you need to pick the almost RLC, and that almost RLC should include the unit circle, right? So what can happen? So that says something about your poles. So that means the almost pole must be inside this unit circle. So when you pick the almost RLC, you will include the unit circle. This is similar in Laplace transform, where we say that your rational function you want to be causal and stable, then all your poles should be on the left-hand side, right? So this is a similar thing. It says you want to be stable and causal, then all your poles should be inside the unit circle. So when you pick almost RLC, you will also include the unit circle. Okay. So this question about this example. So this is how you analyze stability and the causality for the transform. And let's see a little more example. So this is the system function for second system, which we skip the derivation, but it has this form: 1 over 1 minus 2 r cosine theta z minus 1 plus r squared z minus 2. And you can solve the second equation here, and you see that it has two poles at r equal j theta and r equal minus j theta. And then we can solve this system. Well, obviously this doesn't include RC, so we need to use more condition to solve for the RC. So maybe let's say we assume initial rates condition and we have causality. Excuse me. So if we have causality, then as we know, the RC should be almost 1. Okay. And so the Poisson plot will look like this. So it depends on whether r is bigger than 1 or r less than 1. So we have r e to the j theta and r e to the minus j theta, so two poles here. And as we say, the RC should be the almost 1. And so if r is less than 1, is small r is less than 1, then your this causal almost RLC will include your unit circle, then it's stable. And if r is bigger than 1, then your pole is outside your unit circle, so your causal system is not stable. And yeah, and that should be consistent with, so if you read chapter 6, that should be consistent with your analysis in chapter 6, which says that your r less than r bigger than 1, then your system becomes stable, etc. Okay. And okay. And finally, we go to our favorite section in every chapter, that's solving differential or difference equation. Okay, so let's see how we use the z transform to solve our linear constant coefficient difference equation. And well, they're basically doing the same thing as usual. So you take your linear constant coefficient difference equation, so say like this, and you just apply your transform on everything. Alright, so and this will be very similar to the Laplace transform one, except now we can deal with the unstable system. Okay, and yeah, so you apply the transform on everything. Excuse me. And then this time shift here, then so z transform everything, so obviously y become big Y and x become big X, and then you have those time shift, right, because you are taking difference equation, and those time shift you can just deal them with well, the time shifting property. So x of n minus n0 become z to the minus n0 x of z with something changing ROC, but that's nothing about it for now. So yeah. So you see that this minus 1 just give you z to the minus 1, and this minus 1 give you z minus 1. And so actually you can get the polynomial of z minus 1 here, and the polynomial of z minus 1 here, times big Y and times big X. So you move things around, you see big Y is big X, times this rational function of z minus 1. Okay? And yeah. And then you move x to the downside here, then we got our favorite h is big Y divided by big X equal to this rational polynomial of z minus 1. And obviously it can be written as a rational polynomial of z also. Okay. Yeah, so we get our system function as this rational polynomial, sorry, not rational polynomial, it's rational function of z, or z minus 1. And but this is incomplete. And well, just as usual, this is because the difference equation, you want to solve it, you need to supply other conditions, right? So yeah, so you need to supply maybe initial condition, or saying something like they are causal or stable, etc. And those conditions will determine your RC, etc. Okay, and yeah, yeah. So for LTI system, you need to supply extra conditions to determine the ROC. Okay, okay, and well, if you look at this function, then I think there is one pole at z equal to 1/2. So, so there are two possible ROC here. Okay, so we should highlight it. Oh, actually we don't need it. Okay, so yeah, as we say here, so there are two possible ROC because there is a pole at z equal to -2, z at 1/2. Okay. So one ROC is z bigger than 1/2, and another ROC is z less than 1/2. And let's just try to solve both of them. Okay, so for z bigger than 1/2, and we solve this in kind of a funny way. Okay, I guess the way we do this before is you do partial fraction expansion, but so you do division and do partial fraction expansion. But here we do this in kind of a bit smarter way. So we think about this as 1 plus 1 plus 3 z minus 1 times this thing that we already know, this partial fraction we already know. And why are we doing this? Because we kind of do this by linearity. So, yeah. Because the time shifting property is really nice here. So this one term, obviously, it just is 1 over 1 minus a z minus 1 thing. So this one term, we can just use our favorite example to invert it back to this 1 over 2 to the n, and times u to the n. And this 1 over 3 z minus 1 term, we can actually just use time shifting property and get all the answer. Okay. And okay, yeah. So this 1 over 3 term, we use the time shifting property. So if you don't have this z minus 1 here, then you get also this 1 over 2 and u to n, right? And by this example, so if you want to get hr z minus 1, you just should take x over n minus 1. So you get hr n minus 1 here. So 1 over 2 to n minus 1 and u minus 1. Okay? So we do this a little smarter way. Okay. And so that's h of n. Okay. And and yeah, so that's the ROC for z bigger than 1 over 2. And then there's another ROC for z less than 1 over 2. But we basically can do the same thing. So the first one is the same form. So instead of verify, you use so instead of 10.1 example, you get 10.2 example. So you just get this left-sided exponential function. And then this z 1 over 3 z minus 1 term will still give you a time shift. Yeah, still give you a time shifting n, and so you still get this n go to n minus 1 thing. Okay. And yeah, and yeah, so you get those two possibilities of your impulse response function. So you solve your difference equation, you get your system function in your form, but you need to decide the ROC. And we solve for two possible ROC. So the first ROC, so if you are either causal or stable, then you should pick the first ROC, right? Because it's almost 1. And you also include a unit circle. And if you are neither of those, so then you get the anti-causal and unstable system. Okay. Question. And I guess that's an example with a specific number, but you can think about if you do a general linear difference equation, then you can write the system function as this polynomial of z over polynomial of z minus k with this over polynomial of z minus k, and sorry, I should say polynomial of z minus 1 over the polynomial of z minus 1 with the upper polynomial with coefficient with those x coefficients, and lower polynomial with this a coefficient that's same as a y coefficient. Okay. And they are all derived from this. Once again, I can derive it from this time time shifting property. So all the time shifting here, each time you do time shifting, it just give you z to the minus 1, z to the minus k. So this minus k here give you z to the minus k, etc. Okay, and okay, 10 minutes, so maybe let's finish. Oh, do we have time? Okay, so let's finish the examples. There are a lot of examples. Let's go a little quicker. So next example is we are trying to get the system function from the information given in this question. So we have two information. So basically we have two input-output pair. So first one is we have input being this function we know very well, 1 over 6 to n u of n, and we say output, but the output we don't totally know. Output have some arbitrary a, real a here. Output is a 1 over 2 to n plus 10 1 over 3 to n, that's u of n. And another input output is x2 to n, input being minus 1 to n, and output is 7 over 4 minus 1 to n. Okay. And then from those two things, we can solve for the system function h of z. Okay. And we can also differentiate this a. Let's see how we do this. And so, as you probably guess, what we want to do is, well, we look at the first one and we want to do z transform everything. So x1 you do z transform is this familiar form 1 over 1 minus a z minus 1 with z bigger than a equal to 1 over 6. And also y is the same thing with a equal to 1 over 2 and 1 over 3. So y is so big y1 is this thing, but we have a arbitrary a coefficient here. Okay, and then there are a lot of calculation you can do. You can multiply all the y, and y is this rational function, and well, its RC is almost RC, so it's outside the point 1 over 2. And finally, we can write our system function. So it's big Y divided by big X, and so it's all these things with divided by big X. So over this thing becomes times this thing. So we're writing things in terms of polynomial z minus 1. And so if you know A, then we already determine H. Okay. So the hard part here is we don't know A, so we are writing this H as a function of A, and we need to decide A later. And how we decide A later is we use the second equation. Okay. So the second equation we don't actually need to do. I guess if you really want, you can do the transform, but there is an easier way to see this, because this is the eigenvalue equation for your LTI system. So remember this is minus 1, so this is z equal to minus 1 to the to the n, right? Remember, z to the n is always the z to the n is always the eigenfunction of your LTI system. So it just says the input is minus 1 to the n with z equal to minus 1. Then output is also minus 1 to n times the eigenfunction 7 over 4. So, and then we remember this eigenfunction is just h of z. Okay. So h of z, so x2 is input x2 is z to the n with z equal to minus 1. Then output is h of z times z to the n, so with z equal to minus 1. So so all the thing you want to say is h of minus 1 equal to this h of 7 over 4 here. So h of minus 1 equal to 7 over 4, then we can solve for a, right? Because we have h of z with this indeterminate a here, then we can just plug in this minus 1 equal to 7 over 4 point. So you have z equal to minus 1 here, then here we get some function of a, and then here we get 7 over 4, then you can set for a. And hopefully we do everything correct, then we get a equal to minus 9. And yeah, then you plug your a equal to minus 9 back, and finally you get your h of z equal to something. And we figure out equal to this thing. Is a polynomial of z minus 1. Okay, so yeah, so here we solve for h of z already. That's kind of answer, and but we can turn it into other forms and say a little more. So let's say we multiply all everything and also turn into a polynomial of z instead of polynomial z minus 1. And oh, okay. So there is one actual thing we need to determine. That is, we need to determine RC of h. And this is actually also possible from the C we know, because when we do this y from y divided by x, we are basically doing convolution, right? We know the y1 is convolution with small h and with small x. And because we know the time domain of y1 and x1 exactly, and so we have a ROC here. So ROC of x1 is z bigger than 1 over 6, and ROC of y1 is this z bigger than 1 over 2. And so maybe let's draw a little thing here. And okay. So we have y1 equal to h times x1, right? And we think about ROC of y1. So there is a 1 over 6 and there is a 1 over 2. And so the x1 ROC is bigger than 1 over 6, and y1 ROC is bigger than 1 over 2. And from this thing, we know the ROC of y1 should be like at least the intersection of so that is R1, R2, RH. Okay. So R2 is at least RH intersection with R1. And what does this say? This says that so so we look at this H, and it has two poles at 1 over 3 and 1 over 2. So okay, so that's back here. So okay, it's annoying. It's 1 over 2 and 1 over 3, right? 1, 2, 1 over 3, 1 over 6. And so we think about the ROC of this bigger than 1 over 6 and the intersection of all three possible ROC. So it's either this ring between 1 over 2 and 1 over 3, or less than 1 over 3, or bigger than 1 over 2. And yeah, so intuitively only the bigger than 1 over 2 intersection makes sense, because intersection with this bigger than 1 over 2 with this bigger than 1 over 6, they immediately get this bigger than 1 over 2 thing. And also the other two is not possible, because say if you have this ring between 1 over 2 and 1 over 3 intersection with bigger than 1 over 6, then you will have some ROC between 1 over 3 and 1 over 2, right? And but in your final C of y, you only have the bigger than 1 over 2 part, so you cannot have any ROC between these. But you know the ROC of y should be bigger than this intersection. So yeah, so that should not happen. Okay. Yeah. So you cannot pick any ROC that has this between 1 over 6 and 1 over 2 part. So yeah. So this ROC and this ROC are not possible. This is only possible ROC. So your y you got this y ROC from this intersection of bigger than 1 over 2 and bigger than 1 over 6. Okay, so question from this example. Oh, we actually don't have time to finish our examples, but okay. Let's finish this example anyway. So yeah, so finally we can look at our system function a little more. And so the ROC include unit circle, so this is stable. And also the ROC is almost 1, so it is causal. And also we can write down we can kind of invert this back to a difference equation, right? This polynomial of z minus 1 over polynomial of z minus 1, then You can invert it back to a difference equation by just matching the coefficient here. So these go, the upper side go to the x1 and the lower side go to the y1. Okay, and we have 1 minute. We don't have time to finish this, but so I guess this example is still in the test. So yeah, so we are just on time. So unfortunately we don't have time to finish everything, but I think the lecture note is pretty good. So this is a little update so for then what I had on the website for now. So I will upload this later today. So you can look at this example, and obviously this is in the test area. And so yeah, so this is a pretty interesting example of you can check all the properties by knowing from from saying that we know we have a stable and a causal system function with poles at somewhere and 0 at somewhere, and they check whether these properties are true or not. And yeah, so this is the exam area. You just need to read it yourself. And I guess all the other parts are not exam area, but you can also read the unilateral the transform you are interested to see how you solve the initial value problem. Yeah, so I guess extra 1 minute about unilateral the transform is similar to a unilateral Laplace transform, where you are doing the summation from n equal to 0. So once again you are cut off all the less than 0 part, and then when you take the shifting property, then you get this unilateral z transform, get this weird form of z minus 1 times this xo minus 1, and this xo minus 1 term will help you solve the initial value problem. Okay, so I think that's not in the final exam range, but if you are interested, you can read the lecture notes. Okay, so sorry for overtime. As usual, next Friday will be final, and this week we'll still hand out homework, but you don't need to turn in. And also next Tuesday will be final review. Okay, so see you next week.